The last type of hypothesis test that we're going to go over is if we're only interested in if a subset of predictors are useful. So this is a partial F-test. In other words, we might be interested if the partial effect of several predictors as a group are significant in explaining the outcome given the other variables in the model. So we won't include those other variables as differences between the reduced and the full model. So essentially, we want to find out if a group of predictors taken together influence the outcome. And like I said, what we'll do is we'll have a reduced model where we have, all of the variables that we don't think have any influence. And then we'll include the variables that we're interested in, the ones that we want to see whether or not they're useful. And that'll be our full model. We'll set up our hypothesis test then such that our null is that these variables that we're interested in, we will anticipate that they have no relationship. So our alternate will be that at least one of them as a group collectively are useful in explaining variation in the outcome. So our test statistic will be the regression sum of squares from the full model minus the regression sum of squares of the reduced model over the number of covariates that are in the subset that we think are useful over the residual sum of squares from the full model over n minus the number of covariates in the full model, including the ones that we may or may not be interested in, minus k. Now we can rewrite this expression as the residual sum of squares from the reduced model minus the residual sum of squares from the full over the number of covariates that we're interested in the subset over our estimate of sigma squared. Again, we're going to be referencing the F distribution, which has two different degrees of freedom. So remember, P is the number of variables we want in that subset, and the other degrees of freedom in the denominator is going to be using n minus k, which is the number of variables in the full model, including the ones that we may or may not be interested in. So going back to our example with support for Bush going into Iraq before the war, let's just see whether or not our variable for white has any impact on support for the war. And we can do this by first setting up our full model with white, and that's going to be auto results, and then we have our reduced model, which does not include that variable. We can then run our partial F test using ANOVA. We get our RSS and TSS. We can construct our F statistic then, or in this case, it'll just give it to us. We get 0.735, and if we did this in R, we could calculate it, but it also provides the p-value, and we get a p-value of 0.39. Therefore, we cannot reject the null hypothesis that this subset has no relationship. Therefore, right, it seems like there is not a relationship here between being white and supporting Bush going into the Iraq War, which we would have gotten from the t-test before. We can again do this for party ID, where we remove party ID from the reduced regression. We do our partial F test with the ANOVA, and lo and behold, just as before, we get an F statistic that's quite large and a p-value that's quite low, which allows us to reject the null hypothesis that there is no relationship between this subset, in this case, party ID, and our outcome of interest. Again, this is the exact same result that we would get if we did an individual t-test. I just want to drive this home because it's essentially a couple of different ways at looking at the same thing from different angles. As I stated before, we can not only do the partial F tests like I just wrote using ANOVA, we can express them using our R squared, where the R squared is the sample multiple correlation coefficient that we obtain with the full model, remembering that K is all of the variables and P is the number of variables that we have in our subsetted model. And again, the null is stating that the specified variables have no relationship with our outcome. And we can rewrite our F statistic as such, and we can get it in R with this. I don't want to go over too much of what's happening here. You can go over it in more detail if you want. All this to say that there are a multitude of different ways in order to generate your F statistic, whether you want to use ANOVA or whether or not you want to break it down by the component parts with the residual sum of squares and the total sum of squares and your estimate of sigma square, or if you prefer, once you have those things, to just use your R squared value as well. It doesn't really matter, you'll get the same thing. So just as a brief review, we talked about 3 different ways that we can go about interpreting whether or not relationships and multivariate regressions are discernible from 0. And we did that using first individual t-test of individual estimated coefficients using the standard errors. We also did overall or omnibus f-test, in which case we're interested in whether or not any of our covariates have a relationship with our outcome. And we also talked about partial f-tests, where we may be interested in whether or not a subset or a group of variables has an impact on our outcome. And hopefully what became really clear throughout the entire process was that there are many different ways of doing the exact same thing, and it's not necessarily a bad idea to double check your work with one or the other.